All right, good morning, everyone. So, a couple quick reminders. Again, exam number 2 is exactly 1 week from today. So we still have a lot to cover before that happens, but we'll see how far we get. The other thing is, after class is over, I will then post conceptual questions number 7, I believe it is, which will be due tomorrow by 5 p.m., depending on how far we get today. So that's pretty much it. I also haven't posted the solutions for the practice stuff yet, so I'll probably do that either Monday or Tuesday next week, give you a little bit more time to work on those. So I had a great question the other day, which I was going to talk about yesterday, but I forgot because I'm old and I forget things. So anyways, the question is, again, how should we prepare ourselves for the exam since the homework is not required? And basically my answer for that was anything that you are not quite sure about or don't feel comfortable about, do a few of the homework problems. And the homework problems are there to get you more comfortable with that type of material, to understand it a little bit further. Once you have a better grasp of what's going on, leave the homework, start working on the practice exam. Because practice exam stuff is closer to what you're going to see on the exam itself. The homework is mostly there just to get you more comfortable with the ideas. So if there's anything in class that we've gone through, like the integration, things like that, that you're not that comfortable with, do a few problems on Pearson. Got to become a little more comfortable with it. Once you feel a little bit better, then start working on the practice stuff. So good. So today, as I mentioned before, we're going to start talking about probably the most conceptually difficult thing we're going to talk about in this class. Not the most. It will get a little bit worse than this, but the most difficult at this stage anyways is what's known as Gauss's Law. So what's Gauss's Law? So Gauss's Law is an alternative way of determining the electric field. So as we talked about before, what we've had is what? Now Coulomb's Law. Coulomb's Law says that the electric field is equal to K times the integral of dq over r squared, typically in some sort of r hat direction. But as I mentioned in class, the problem with this is that, 1, it can be a very highly complicated integral. 2, it could be an integral that we can't do at all, which means 3, we'll have to actually numerically do this, okay? So it turns out that we can do this new thing, which is called Gauss's Law, where Gauss's Law is an alternative way of actually defining the electric field, which turns out doesn't involve an integral. However, we'll define it in terms of an integral, but the point of doing Gauss's Law is you never ever have to do the integral. And I'll tell you how we're going to do that and why we're going to do that. But the only problem with Gauss's Law, at least as far as this class is concerned, is it is highly dependent on symmetry, which means Gauss's Law only works in 3 scenarios. If I have beautiful, perfect spherical symmetry, if I have cylindrical symmetry, where the object is infinite in length, it can be spherically symmetric, but not infinite in length, then Gauss's Law doesn't work. So it has to be cylindrically symmetric and infinite in length, or if it has planar symmetry. Those are the only 3 cases that Gauss's Law works. If those things are satisfied, Gauss's Law is a nice, quick, beautiful way of actually coming up with the electric field, where for the most part, you never actually have to do an integral. So, but to get to Gauss's Law, we'll have to massage our brains a little bit. Okay, so things become a little bit difficult. So to talk about Gauss's Law, the first thing we're going to have to talk about is what's known as flux. Let's talk about flux. Now, to talk about flux, what I'm initially going to talk about is actually not flux when it comes to electric fields, but actually flux when it comes to fluids. So I'm going to talk about fluid flux. You've already actually seen this in 205 when we talked about volume flow rates. It's actually known as volume flux. But to kind of get it motivated, I'm going to show you a video that I made last night. So if the quality of this is not that great, I apologize. Actually, I had to run to the store and buy more bubbles because my kid spilled it all over the floor. That was great. So you may hear screaming in the background. I'm not sure. That's my kids with my wife trying to go to bed. It's always a battle. So anyway, so basically what I have here is my favorite blow dryer, because I blow dry my hair every day after I take a shower. So what I'm going to do is I'm going to turn on the blow dryer. I'm not going to say anything in the video because I noticed last time I made the video I talked way too much. So this time I don't say anything. So basically what's going to happen is I'm going to hold this wand here. So the wand has a bubble. I'll show you that in just a second. I'll blow through it. I'll zip it back in. And then what I'm going to do is I'm going to turn on the blow dryer, which is then going to run through the wand. But initially no bubbles will come out. But then what I'll start to do is start to rotate the wand. So as the wand starts to rotate, hopefully you can see the bubbles actually start coming out. And this is actually volume flux, and we'll talk about this. Here's my bubble, great. For some reason, I kept doing this very low. You guys see the bubbles? Do it one more time. I realized I was too far on the bottom of the screen. There we go. And there's the ball. Okay. So nice, short, quick video. No screaming kids. I'm very excited about that. Good. We want you to play. Go away. Okay. So this is what we called volume flux or volume flow rates. So what is volume flux? So notice here what I'm doing is I'm taking my blow dryer. So here's my blow dryer. My blow dryer then is shooting out wind, so air, which is say blowing in this type of direction. So what I'm actually doing is I'm creating a vector field of wind velocity. Right? So what's happening here is I have a whole bunch of wind which is blowing in this direction, which is creating a vector field. That vector field is what we're going to call the velocity field. Okay? Now initially, I have the wand. So initially here's the wand, where the face of the wand is going to be perpendicular to the direction of the wind. Okay? So initially what's happening is all the wind is blowing across the surface of the face of the wand, right? It's doing this. So that basically none of the velocity vectors here are penetrating inside of the area. Zero, right? So initially when the wand is like this, we have what's known as zero flux. So the flux is equal to 0. So phi here is what we call the flux. So this is volume flux. So now what? So now, as I take my blow dryer, and these are actually not the worst pictures I've ever drawn, so this is pretty good. So here's my velocity. So now what I'm going to do is I'm going to start to rotate the wand. So what happens now is the face of the wand no longer is going to be perpendicular to it. It's now going to start to become at an angle. Right? So now what happens is now my wand face is now going to be rotated such like this. Now what's happening is some of these velocity vector fields are actually now passing through the wand itself. Which means in this case, I'm now blowing bubbles, which means the flux through the wand is not equal to 0. Right? So as I start to rotate this thing, the flux, the amount of velocity field lines which pass through the surface of this wand, is no longer equal to 0. Okay? So if I think of this as a velocity vector field blowing in this direction, we could then say the flux is basically equal to the number of field lines which pass through the surface of this wand. This is what the flux actually means. So flux, by definition then, is equal to the number of field lines. Running out of room here, let me erase some stuff. Which pass through the area. So this is how we define flux. So flux then, in this case, is the number of field lines, in this case, velocity field lines, which pass through the surface of the area. So how do we define the area then? Well, either remember or learn it the first time, we can classify any area as a single vector which points perpendicular to the surface of that area. So this is my area. I can then classify this area as a single vector which points perpendicular to that surface whose magnitude is equal to the area of that vector. Okay? So the magnitude of this vector is equal to the area of the actual object. Now, I'm going to point out now, even though it's going to be unimportant in just a minute, there is actually an ambiguity to this. Because this area has two different ways I can point that vector. Now, as far as we're going to move forward, it's going to turn out we don't care about that ambiguity, but when we come back to flux, which we're going to see flux again when we come back to magnetism, that's going to become important. So how we define the direction at which we're going to write that area vector is going to be dependent. But in this case, just note that there is an ambiguity because it could point this way or it could point this way. How do I define which one is which? For now, it doesn't really matter. So what this means then is I can actually classify this area here as a single vector, which is perpendicular to the surface of that area. So here I can say, well, initially the area vector is pointing this way. So this is my area vector. But now as I rotate it, what happens then is that the area vector now points this way, which means that now there's an angle between these two vectors. So let's call that angle theta, where initially this was at an angle theta of 90 degrees. So initially, I had zero flux because the area vector was perpendicular to the velocity vectors. But now I have zero flux because now the angle is no longer 90 degrees. It's either less than 90 degrees or greater than 90 degrees, depending on how I look at it. So using this, we can then write down what's known as volume flux, or also known as volume flow rates, or when you guys take fluids in the future. We can then say that the volume flux is then equal to the velocity vector dotted by the area vector, which is then equal to the magnitude of the velocity vector times the magnitude of the area times cosine of the angle between the two. Where again, this area here is specifically the area which is perpendicular to the face of the area whose magnitude is equal to the area of that surface. Okay? So this is what we call volume flux. So again, what the volume flux says, or what it counts, is the number of field lines which pass through that particular area. So again, when these two are 90 degrees from each other, what that means is that zero flux lines, or zero lines pass through this area, which means I have zero flux. As I start to rotate it, I'm going to increase the amount of flux until this guy is parallel to the field lines, or anti-parallel. Either one doesn't really matter. In which case, I get the maximum amount of flux. So this is what we call flux. So physically, all flux is, it counts the number of field lines which pass through some particular area. That's it. So from here, we can now define what's known as the electric flux. So if we use this flux here, the volume flux, as our reference for then electric flux, we can then say, well, electric flux is the same thing, except now instead of having velocity vectors, I now have electric field lines. That's it. Okay. So we're going to say that what's known as the electric flux, we're going to call that P sub E, is then equal to the electric field dotted by the different, or by the area, which is the same thing then as the magnitude of the electric field times the magnitude of the area times cosine of the angle between the two. So this is what we call electric flux. But notice here we're making an assumption. Actually, we're making two assumptions. So let's talk about assumptions here. Assumption number one is that the area is flat. So we're assuming that this area, like the wand that I was using here, is some flat area. Does that always have to be true? Of course not, it could be bent. Assumption number two is that the electric field is constant. Do I have to have a constant electric field? Of course not. I know that's what? The electric field of a point charge is position dependent, for example. Okay. So even though we now define the electric flux this way, as the electric field dotted by the differential area, there are two assumptions that go into this. The first one is that the area is flat, and the second one is that the electric field is constant. What happens if one or both of those is not satisfied? What do we have to do in that case? Well, in that case, what we have to do is, so let's say I have electric field lines that are actually doing something like this. So that these are non-constant. And let's say I put an area in here where that area is also non-constant. So this is non-flat area. So how do we calculate the flux in this case? So what do we do here? What we're going to do here is we're going to chop this thing up into a whole bunch of small areas. So basically what I'm going to do is around each one of these electric flux lines, I'm going to cut out a small area where this has a amount of area delta A1, so that here my delta A1 might point off in this direction. So this is the magnitude or the vector delta A1, so that this angle here is the angle theta 1. Then by this electric field line, I'm also going to cut out a differential area, or a small area, so that this is delta A2 vector, so that this is also at an angle. Let's call that theta 2, and etc. So we're just going to chop this thing up into a whole bunch of small delta areas, calculate the flux through each one of these small delta areas, sum all those guys together. So in this case, then, we're going to say the total electric flux is equal to the electric flux through the first area, plus the electric flux through the second area, plus blah, blah, blah. I'm going to cut this up in two. So that this is going to be equal to, then, the electric field, 1, dotted by differential area, or sorry, I keep saying differential area, because we're going there. Anyways, small amount of area, delta 1, plus the electric field 2, dotted with area 2, plus blah, blah, blah. Okay. So that this is going to become equal to the sum over I of electric field I dotted with delta I, or delta AI. Okay. So I'm just chopping this thing up into some number of delta areas. Now what we're going to do is we're going to take the limit that each one of these delta areas becomes infinitely small. So this is going to become a differential area. So finally, what we're going to say is that the total flux is then equal to the limit as delta AI goes to 0 of then the sum over I of electric field I dotted by delta area I. You guys already told me this before, but what happens if I take the limit of a sum? What do I get? An integral. So this thing finally becomes the integral of the electric field dotted by the differential area. This is what we call the flux. So the electric flux, by definition, is in general equal to the electric field dotted by the differential area. So what's a differential area? So again, if this is my area that I'm looking at, the differential area is a small amount of area that points in a particular direction, dA. Meanwhile, the electric field is going to point in some direction. So let's say here's my electric field. So my electric field is also a vector. So notice what the dot product does, again, is that it turns this vector into actually a scalar. So remember, the point of a vector, or point of a dot product, is to turn these guys into scalar quantities. So the right-hand side is a vector dotted by a vector, which is actually a scalar. So in this case, I'm simply integrating over the scalar. Okay? So this is what we call electric flux. But what we're going to be interested in is not necessarily electric flux by itself. What we're going to be interested in is the electric flux throughout a closed surface. So this is actually what we're going to take as the electric flux. So what does this circle mean? So this circle means that the integration that we're going to be doing is the integral over a closed three-dimensional surface. That's what this circle means. So this is actually what's known as a closed surface integral. So what this means is we're going to have a three-dimensional object. Here's my three-dimensional object. And we're going to be integrating over the surface area of this three-dimensional object. So this is actually a surface integral over the 3D closed surface. So this is actually what we're going to use to define flux. Now here, what is dA again? So this is where the ambiguity goes away, because again, what I'm doing is I'm not integrating over a one or two-dimensional surface like this anymore. I'm now integrating over a three-dimensional surface like this, okay? So in this case, I no longer have the ambiguity, because now what we're going to say is that that differential area always has to point outward away from the surface. Okay? So what dA is going to do now is dA will always point outward away from the surface of the object. So dA is an outward pointing vector. So this is what we call the electric flux. So the electric flux is, again, the number of electric field lines which pass through a three-dimensional object. So through the surface of a three-dimensional object. So what we're defining as electric flux here is then the number of electric field lines which pass through the surface of the object. So this is what the electric flux counts. So the electric flux simply tells me the number of electric field lines which actually pass through the surface of this object, where the area vector is always outward facing, which means that dA here points in this direction. But if I looked at a dA on this side, so if I cut out this section, dA would actually point in this direction. If I look someplace here, dA would point in this direction. Someplace over here, dA would point in this direction, and etc. So dA is always a vector which points away from the surface. Now, why is this important? Well, this is important because we have a dot product. The dot product, remember, tells me comes inherently with a cosine of the angle, which means if I have electric field lines coming in to a surface, the area vector points in the opposite direction. That means I get a cosine of 180 degrees, which means I get a -1. Where if I have electric field lines which are coming out, in that case, I get a cosine of 0 degrees, which means I get a positive value. So what does that mean? So what that means is if this was my three-dimensional surface, and this was my electric field lines which are passing through this surface, what's the total flux through the surface? So what I want to know in this case is what is the total flux? Well, again, in this case, over here, my dAs are pointing in this direction, right? They're pointing outward. My electric field is pointing inward, which means all of the flux lines on this side are all going to account for negative fluxes. Right? So anything on this side, since all my dAs are pointing outward, my flux on the left-hand side here is simply equal to some negative value. So this is going to be less than 0. That's greater than. This is going to be negative. But what's happening on the right-hand side? Well, on the right-hand side, all my dAs are pointing outward, which means that now I have a positive cosine, which means on this side, what will happen then is all my dAs are going to point in the same direction, or at least relatively the same direction as my electric field, which means the flux on the right-hand side then is positive because this guy is greater than 0. So anywhere I have flux lines coming in, they have to be negative. Anywhere I have flux lines going out, they have to be positive. But how many flux lines do I have on this side? How many electric field lines do I have on this side? 3. How many do I have on this side? 3. So if the flux simply calculates or tells me the number of field lines which are going in versus going out, or the number of flux lines which are passing through the surface, if I have 3 flux lines on this side which are negative, I have 3 flux lines on this side which are positive, what's the total flux? 0. In this case, the total electric flux must be equal to 0. So what the hell does that tell me? Well, that tells me that anytime I have an equal number of flux lines coming in versus coming out, I'm always going to have a total flux equal to 0. Great. Now let me ask you a harder question. How can I then get a scenario where I have an unequal number of electric field lines coming in versus going out? Because that's going to be more interesting. Because otherwise, if I have the same number coming in as I have coming out, my flux is always going to be 0, which is telling me nothing. It just tells me I have the same number coming in versus coming out. There's no way I can extract the electric field from there. But what's more interesting is how is it possible for me to have an unequal number of field lines coming in versus coming out? What must be the condition for that to be true? What has to be present? What has to be present? What do you think? This is the major idea of Gauss's law. The key thing that we have to kind of understand at this stage. What is the only way I can create a non-zero flux? What has to be present, and where does it have to be? Let me ask you a follow-up question. What creates electric field lines? Charges, right? So, what has to be present? Electric charge. Great. Good. Where? That's the more important question. What's that there? Inside the object. So if I now have, instead of just electric field lines passing through this thing, if instead I put a point charge or some sort of charge configuration on the inside, what happens in this case? Well now, what color haven't I used yet? We'll stick with blue, I guess. Now I have electric field lines which pass like this, which means that now I have to have all electric field lines going outward, or if it was a negative charge, they would all be coming inward, which means there would be nothing doing the opposite. So the only way to have a non-zero flux is if charge is present and charge is present inside of the object itself. This is the only way to create a non-zero flux. This is Gauss's law. What Gauss's law says is that the flux through any surface must be directly proportional to the charge enclosed inside of that surface. This is Gauss's law. Okay? So what Gauss's law says is that the only way to create a non-zero flux is if that flux is proportional to the charge enclosed in the surface. Okay? So this is the essence of Gauss's law. Now, to make sure that the units on this side are exactly equal to the units on this side, what we have to do in this case then is put in a constant. That constant, all right, that says little q instead of capital Q, is epsilon naught. So what Gauss's law says is that the total amount of flux through any surface is equal to the amount of charge enclosed divided by epsilon naught. Now, what's more unique about this, let's talk about this more in depth, is that notice this side only says that the amount of flux through the surface is equal to the amount of charge enclosed, which means that the amount of flux through any surface is independent of the shape of the surface. All right? So this overall statement says that the flux is independent of the shape of the surface. This is a big deal. And we're going to use this to our advantage, and I'll show you how when we get there. All right? Why is this a big deal? So this is a big deal because, let's say I have a single point charge sitting here. What Gauss's law says then is that what? If I draw this shape around it versus this shape around it versus this shape around it versus this shape around it, the flux through all of those different shapes is identically the same. This is what Gauss's law tells me. Because the flux only depends on the charge which is enclosed, not the shape at which I draw. It is completely arbitrary. So what this means then is that the flux through the black shape is equal to the flux through the gray shape, which is equal to the flux through the green shape, which is also equal to the flux through the yellow shape. All of these are exactly the same. So why is this? Well, again, what Gauss's law says is that the integral of the electric field dotted by the differential area over a closed surface is equal to the charge enclosed divided by epsilon naught. Remember that the electric field goes as 1 over r squared, the area goes as r squared, so this is effectively an r squared times 1 over r squared, but what happens to the r squareds? They cancel, which means that it has 0 distance dependence to it at all. Right? So this guy we know is proportional to 1 over r squared, this guy is proportional to r squared, which means these two cancel, which means the left-hand side is simply a constant, and it's equal to a constant right-hand side. This is the beauty of Gauss's law. So what Gauss's law says is I can determine then an electric field as long as I have charge enclosed inside of that electric field. That's what's creating our electric field. We'll talk about how this actually works in a second. So let's do an example before we move on. So my example says that I have a cube of side length L that's placed in a region of uniform electric field. Find the electric flux through each face of the cube and the total flux through the cube when it is oriented so that 2 of the faces are perpendicular to the field. So let's draw. So let's say here's my cube. There's my cube. Okay. Draw it down here. Here and over here. So let's take, I don't know, this is the z-axis, this is my x-axis, this is my y-axis. And then we know it has a uniform electric field, which means it's a constant electric field, which points in a particular direction, which is perpendicular to 2 of these faces. Whatever faces we choose, it doesn't matter. So we can choose the x and minus x, or y and minus y, or z or minus z. It just has to point in some particular direction. Doesn't matter which direction, find out what direction you want to go. Want to go in the x direction, y direction, or z direction? Y, good. So here, we're going to choose our electric field to be pointing in this direction. So this is our electric field. Good. So in this case, we know our electric field then as a vector is just going to be the magnitude of the field in the j hat direction. Good. So what does Gauss's law say? So Gauss's law says that the flux through any one of these surfaces is going to be equal to the integral of the electric field dotted by the differential area. But here, what do we know? We know that the electric field is constant and each one of these surfaces is flat. Okay? So as long as the electric field is constant and each one of the surfaces is flat, this simply becomes the electric field dotted by the area. That's it. Okay? So this means then that to determine the flux through each face, all we have to do is write each face as a vector area, because we already know the direction of the vector of the electric field, dot those together and then calculate the flux. That's it, not too bad. Right? So let's write each one of these faces as a vector. So I'm going to call this face here 1. So in this case, area 1 points in this direction. Area 2, I'm going to take the behind that, so the area 2 points this way. So that's pointing in the negative x direction. Let's say area 3 is the y face. So I'm going to point it this direction. So this is area 3. So area 4 is going to be the negative y face. That's going to point this way. So that's going to be area 4. And then area 5, let's choose that the positive z direction. So this is area 5. And then finally, area 6 is going to be this one, which points in the negative z direction. So that means then that area 1 is going to be equal to what? The area, which is the length squared, because it's a cube, times the direction, where the direction in this case is simply the I-hat direction. Area 2 is then going to be equal to negative L squared in the I-hat direction, because it points in the negative x direction. Area 3 is then going to be what? L squared pointing in the j-hat direction. Area 4 is going to be negative L squared because it points in the negative j-hat direction. Area 5 then is going to be equal to L squared in the k-hat direction because it points in the z direction. And then area 6 is going to be equal to negative L squared K. Okay? So these are all just my area vectors. So just classifying each face by an area vector. So good. So now from this we can calculate the flux through each surface. So we can say the flux through surface 1 is then equal to the electric field dotted by area 1. Well, we know the electric field is equal to the magnitude of the electric field in the I hat direction dotted by L squared in the, oh, sorry, that was J hat direction. You told me J hat direction. Dotted by I hat. There we go. Well, what's J dot I? That's cross. Or dot, and that's easier. So is X direction perpendicular to Y direction? Yes. So that's 0. Okay. They're not parallel to each other at all. So this is simply equal to 0. Okay. Because J dot I is equal to. Good. What about flux 2? So flux 2 is equal to the electric field, J hat direction, dotted by negative L squared in the I hat direction. That's also equal to 0. Flux 3 then is equal to the electric field dotted with, so that's electric field dotted with area 3. So that's equal to E times EJ dotted with L squared J. But what's J dot J? It's J dot J. My Calc 3ers that just took this in an exam. I forgot about it already. I gave you a hint. Good job, Richie. 1. Good. J dot J is 1. So this is equal to E L squared. Yeah. Electric flux 4, so through the 4th surface, is then equal to the electric field dotted by area 4. So that's is equal to EJ dotted with minus L squared J. So that's just equal to minus EL squared. Flux 5 is equal to 0 because now I have an J dot K. J dot K is equal to 0. And flux 6 is also equal to 0 because I have again, J dot K. So this is the flux through each one of the surfaces. So the total flux is equal to simply the sum of all the fluxes. So the flux 1 plus flux 2 plus flux 3 plus flux 4 plus flux 5 plus flux 6. So this is equal to 0 plus EL squared minus EL squared plus 0, which is equal to 0. So this says that what? The total flux through the closed surface in a uniform electric field is equal to 0. Did we already know that ahead of time? Yes, because there was no charge enclosed inside the surface. Since flux enclosed was equal to 0, well, the charge enclosed is equal to 0, the total flux then must be equal to 0. So good. So again, this is Gauss's law. So again, what Gauss's law says is that the integral of the electric field dotted by the differential area, where again, this is an integral over a 3-dimensional closed surface, where we're integrating only over the surface of that closed surface, is equal to the charge enclosed divided by epsilon naught. This is Gauss's law. Okay. Now, you may be looking at me now saying, you told me in the beginning that the point of doing Gauss's law was not to do an integral. And now you're telling me there's a damn integral. You're lying to me, but I'm not lying to you. I'm going to show you why. Okay? So let's use Gauss's law in a problem and see how this thing actually works. So let's look at a problem. And the problem we're going to look at is, let's say I have a single point charge of charge Q, and I want to know what is the electric field of this point charge. Now, we already know by Coulomb's law told us that the electric field was equal to K times the charge divided by R squared in the R hat direction. Which means when I do Gauss's law, I better get the same damn answer, otherwise it's wrong. Okay. So let's look at this. and let's talk about it. So first of all, we know that the electric field is going to point radially away in all directions. So this is my electric field. Now, again, what Gauss's law says is that Gauss's law says that the flux through any surface is equal to the total charge divided by epsilon naught. But, again, the surface at which I choose is completely arbitrary because it doesn't depend on the surface at which I choose. What does that mean? What that means is, what we're going to do is we're going to draw a hypothetical object, which is what's known as a Gaussian surface. That Gaussian surface at which we're going to draw is the figure that we're going to use to calculate the flux through. Since it's independent of the shape of the object at which I draw, that means I get to choose the shape at which I want to use. This is where the non-integral comes from. Because I get to choose, what I want to do is choose a shape which makes the integration as easy as possible, i.e. not do the integral. Because I want to choose a shape that matches the symmetry of the problem. What does that mean? What that means is if I have a point charge, and I know that the magnitude electric field here is the same as here, which is the same as here, which is the same as here, which is the same as here, what type of symmetry does this problem have? So if I go all directions the same, what type of shape is that? A circle or three-dimensional, a sphere. This thing has spherical symmetry to it, which means the Gaussian shape I want to draw is a cube. No, I'm kidding. It's a sphere. Because it has spherical symmetry to it, I want to use the fact that it has that spherical symmetry to it, choose a Gaussian surface which is a sphere. That way I can use the fact that the electric field is constant everywhere along that sphere. If the electric field is constant everywhere along that sphere, what that means is that electric field contribution comes outside of the integral, which means my integral of E dot dA is no longer the integral of E dot dA, it's simply E times the integral of dA. Well, what's the integral of dA? A is the surface area of that object, which means that the left-hand side of Gauss's law simply becomes E times A. You never have to do the integral. This is what's beautiful about Gauss's law. So unlike Coulomb's law, where I definitely have to do that damn integral, here I don't have to, as long as I choose a shape which matches the symmetry of the problem. Now, not all problems have an actual good symmetry to it. And I'll show you an example of that in just a second. Let's finish this one up. So again, what we know is that the magnitude of the electric field here is constant everywhere at a constant radius, which means I'm going to draw my Gaussian sphere, which in this case is this guy. So this thing here is what we call a Gaussian surface. Or in this case, we're going to call it a Gaussian sphere. Now, again, a Gaussian surface, or in this case, a Gaussian sphere, is a hypothetical object that you are drawing. You have complete freedom to choose this. And you're going to choose it based off the symmetry. Here, this thing has spherical symmetry to it, so I'm choosing this guy, and this guy has some radius to it, r. Okay. So good. So how does Gauss's law work? So Gauss's law, again, says that the closed surface integral of the electric field dotted by the differential area is equal to Q enclosed divided by epsilon naught. Now, we're going to come up to a problem, not today, but on Monday, where sometimes the hardest part about this is figuring out what Q enclosed is. For now, it's pretty easy because the only Q enclosed is Q, so that's not a big deal. But sometimes that'll be the hardest part. So from here, let's first look at the right-hand side. The right-hand side is simply Q, because that is the only charge which is enclosed, divided by epsilon naught. So what does Q enclosed mean? Q enclosed means literally the amount of charge which is enclosed inside of the sphere. That's it. Which means if I had another charge, let's say hypothetically I had another charge out here, which was a charge, I don't know, I'll call that Q prime would not show up in this expression. Because Q prime is outside of Q enclosed. It is outside of the sphere which I draw. So Q enclosed literally means how much charge is enclosed inside a hypothetical surface at which I draw. So in this case, if this guy was out here, this guy would not be part, so not part of Q enclosed, because it is outside of the surface, okay? Good, so now let's do with the left-hand side. So first of all, on the left-hand side, we can draw our differential vectors. So here I have a dA, 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 here I have a dA. What can you tell me about the direction of dA relative to the direction of E? So how does the direction of dA compare to the direction of E? It's in the same direction. Right? So E we know points radially outward, dA points also radially outward, so the direction or the cosine of the angle between the two of them is simply 1. Right? So here, since E points this way, dA points this way, angle between the two is simply equal to 0, which means this dot product then becomes E magnitude times dA magnitude times cosine of the angle between the two, but the angle is simply 0, so that's simply equal to 1. So here, automatically, this now becomes the closed surface integral of the magnitude of the electric field times the magnitude of dA. Now, what else do I know? I know that the magnitude of the electric field here is the same as magnitude of the electric field here, which is the same as magnitude of the electric field here, which is the same as here, which is the same as here, which means that everywhere along dA, E is simply a constant. Which means E doesn't depend on dA. Which means what happens to E? It comes outside of the integral. So this is now going to be E times the integral. dA is then equal to Q over epsilon naught. What's the integral of dA? Well, the integral of dA is simply A, but since this is the integral over the surface, this is simply the surface area. Okay? So finally, this thing becomes, switch to another page, E times the surface area is then equal to Q divided by epsilon naught. Which means the electric field is then simply equal to the charge divided by epsilon naught times the surface area of the object. This is the beautiful part about Gauss's law. I never had to do an integral. The only thing I need to know is what is the surface area of the object that I drew. That's it. What's the surface area of a sphere? This may be the hard part. I may not know what that actually is. So anybody know what the surface area of a sphere is? I know we said it before when we talked about how waves expand away from a point source and they decrease because the surface area gets bigger. So we actually talked about it once, but maybe filed back in there somewhere. Go ahead, Dylan. Almost. So it's 4 pi r squared. Very good. So this becomes Q divided by 4 pi epsilon naught r squared. But remember that 1 over 4 pi epsilon naught is simply K, so this is KQ over r squared, which is exactly the same thing as Coulomb's law. This is Gauss's law. The same. So, again, the point of Gauss's law is, as long as we have symmetry, i.e. in this case, spherical symmetry, we don't then have to do the integral. What happens then is Gauss's law simply becomes the electric field times the surface area of the object at which I draw is equal to the charge divided by epsilon naught. Which means the electric field, as I wrote here, is then simply equal to this. This is the electric field, no matter what that configuration looks like. The hard parts here are going to be, what is Q, and what's that surface area? Now, because I have to have symmetry, what this means is that Gauss's law only works for 3 scenarios. So Gauss's law only works for scenario number 1, spherical symmetry. This thing has spherical symmetry. We draw a Gaussian sphere around it. In this case, the surface area is simply 4 pi r squared. That's it. Right. Scenario number 2, it has to have cylindrical symmetry. But again, it has to be infinite in length. So a little more restrictive than spherical symmetry. Okay. In this case, the surface area now depends. It's going to depend on the scenario. So typically, there's going to be 2 different surface areas. So surface area 1 is equal to 2 pi r times L. We'll deal with this on Monday. or the surface area is going to be simply that of a circle, and is going to be pi r squared. Okay? So these are two different scenarios. So this means if I have a cylinder, this is the shaft part of the cylinder, and these are the end caps. That's about it. The last one is then planar symmetry. So these are the only three scenarios at which Gauss's law works. Okay? So Monday, we'll do a bunch of examples of this. Okay? Now, like I said, conceptually speaking, it's a little bit difficult to think about. Mathematically, it's ridiculously easy because it only depends on the electric field times the area. Once we grasp that, Gauss's law is really easy. It's much easier than anything else we've actually done, but conceptually it's more difficult. Okay? So we just have to kind of get past the conceptual parts. Once we get past that, the rest of it's nice and easy. So as I said, Monday we'll do a bunch of examples. We'll show how this actually works in different scenarios, different types of symmetries, things like that. And then I'll get you set up with some group exercises. So we'll be done with all this stuff on Monday. And then that means Wednesday we'll start potentials. We'll be good. So have a good weekend. What's up? Stop this real quick. I'm pretty sure